In this video, we'll use truth tables to determine validity of arguments. So we're going to start with a simple argument and determine whether or not the argument is valid, whether the argument is valid or invalid. If the tank is empty, then I must fill it. The tank is empty, I must fill it. So the first thing we do is we assign P and Q to represent the statements. So P represents the tank is empty and Q represents I must fill it. And now we write the premises and the conclusion in symbols. So the first premise, the tank is if the tank is empty, then I must fill it. We write that as if P then Q. Premise 2 is the tank is empty, so that's just P. And the conclusion is I must fill it, which is Q. Now we write the conjunction of the premises as the antecedent of a conditional statement and the conclusion as the consequent. So here we have if P then Q and Q implies Q. That should be and P implies Q. Fix that. Okay, so now we construct a truth table. Usually put some lines in here. Okay, so here are my P's and Q's, and I know in all cases except P is true and Q is false that P implies Q is true. So T, true, false, true, true. Then P implies Q and P. Well, that means we're asking, is both P implies Q and Q true? So it's only true if they're both true, which is the case with in the first row. P implies Q and Q. Both are true in the first row. But in the second row, they're both false. In the third row, that should also be true. Oh, that should be P, not, there's the problem. That's P, not Q. My bad. But P is false here, so that's false. And again, true and false, so false. But we also know that the only time an implication is false is when the antecedent is true and the consequent is false. So the antecedent is only true here. But Q is true there, so that's true. Here the antecedent is false, and if the antecedent is false, this is always true. So I can just fill in true, true, true. This is a tautology. Final column is all true for all values of P and Q. It's a tautology, and the argument is valid. If you get a tautology in that last column, the argument is valid. Next step. Oh, there it is. Come on. Okay, so the argument pattern P implies Q, Q, P implies Q, and P implies Q is called modus ponens, or the law of detachment. And something like this is always true. We know that P implies Q. We know that P is true. Therefore, Q is true. Okay, so testing the validity of an argument with a truth table is a four-step process. We start by assigning a letter to represent each component statement in the argument. Then express each premise and the conclusion symbolically. We form the symbolic statement of the entire argument by writing the conjunction of all premises as the antecedent of a conditional and the conclusion as the consequent. And then we complete the truth table for the conditional statement. If it's a tautology, the argument is valid, and if not, it's invalid. If at any point you get something incorrect, you get a false statement in that last column, then this is an invalid argument. Okay, here is another example. If our guests arrive before lunch, we'll eat out. We ate out. Therefore, our guests arrived before lunch. So here we choose P to represent our guests arrive or arrived before lunch, and Q is we will eat or we ate out. The argument becomes P implies Q, and Q implies P. So we state that as P implies Q and Q implies P. Well then, the truth table looks like this. Our P's and Q's line up the way they usually do. P implies Q, that's easy enough. Here we have true, false, true, false. This is true if everything is true. It's false if Q is false. It's true if everything here is true. It's false if any part of it is false. So we go over to the final statement and see that, well, what we want here is we just don't want something true to imply something false. Well, true, true, that's good so far, but when we come down here, this is true. P implies Q and Q is true, but P itself is false, and that's false. And it doesn't matter that the other three are true, because this is false. The final column contains a false. It's not a tautology. The argument is invalid. And the way we can think about this is we're looking at this as the argument, if our guests arrive before lunch, we'll eat out. We ate out, therefore our guests arrived before lunch. But this doesn't specify when we ate out. It doesn't say that we had lunch out. It also doesn't say that the only case in which we eat out was if the guests arrived before lunch. P implies Q. It's not the other way around, not in this kind of argument. The previous example used the argument P implies Q and Q implies P. If a conditional and its converse were equivalent, the argument would be valid. Since they're not equivalent, this is an example of the fallacy of the converse. Come on, page. There we go. Likewise, the argument P implies Q, not P implies not Q, is called the fallacy of the inverse. As an example, consider the statement, if it rains, I get wet. It does not rain, I do not get wet. This neglects the fact that you can take a shower when it's not raining. It neglects the idea that you could go to the beach and go in the ocean. There are other ways of getting wet besides raining.